We're going to continue today with our discussion of reductions, how to change the solution of one problem to the solution of a different kind of problem. I want to go over this same idea which I discussed at the end of last class. So far we've been solving problem A by solving a smaller version of problem A. So for example, if we have like divide and conquer or dynamic programming or greedy algorithm, all of those examples in the class that we talked about for first 16 lectures, if we have some problem of size n, what we were doing is developing algorithms that would allow us to phrase that problem of size n as problems of size smaller than n. So in divide and conquer, for example, we would often express the problem of size n over 2. Like in merge sort, we would sort the left side, sort the right side, and then merge them. In dynamic programming, we would solve the version of size k and then extend it to a problem of size k plus 1, and greedy is the same sort of type thing. We had been focusing on algorithms like this type of blue thing, which would take a problem of size n, express it as problems of size smaller than n, take those solutions to those smaller instances, and then map them back to the original problem. So merge sort this would be something like partition or divide, and this would be basically merge or combine. And what we're talking about in this part of the class is how we can extend that idea so that we solve problem A by solving a different problem B, but using the same idea of having this blue algorithm map the big instance to a different instance, solve the different instance, and then map the solution back. So we're talking about the same paradigm, it's just a more generalized. For example, we took a bipartite matching instance, which consisted of left, right, and E, and we would map that into an instance of max flow, which consisted of a graph and a set of capacities. And so if we were to draw our diagram, we would say, let's take instances of bipartite matching. Our blue algorithm is going to transform this instance into an instance of a graph with capacities C. We're going to use any algorithm we know to solve this instance of max flow. For example, we could use Ford-Fulkerson, and that would give us a flow. Now, flows aren't natural solutions to bipartite matchings, but our algorithm would take that flow and map it back to a matching. And you've had examples like this for homework 7, all three of those examples where taking instances of problems, mapping them to bipartite matching or some other type of flow. So in general, if we have instances of problem A, we are now going to look at algorithms which take those instances of problem A and then map them into instances of problem B. We're then going to solve this using any solution problem B. In fact, we might even not know that there exists a solution. Right? In the cases that we've talked about with bipartite matching and flow, we actually had specific examples of solutions to flow. But this theory is so general that we can even talk about problems for which we might not have a solution to B. Why would we want to do that? Because this type of argument gives us a way of saying problem B is as hard as solving problem A. This idea of a reduction lets us compare the difficulty of problems, even for problems where we don't know of a solution. So let's go through a few examples. I started last class with this party problem. So as you venture off after you graduate, eventually you might find a partner, you might want to get married, you might invite some of the people in this class, hopefully I might also be invited, I love weddings. And then you're going to encounter the following social problem, which is that these are the friends you've made through your life, and some of them are not friends. So let's represent that with graph theory, the thing I know that you all love. If we have a bunch of friends right here, we can draw an edge between people who do not get along. And the idea is to find a set of people that you can place at a dinner table. So let's say your wedding was a small affair and you only had one table, and you're just deciding which among these set of friends you're going to invite to your very quaint small wedding. So the problem is, find a set. The problem is to find a largest set of people who get along in this graph. And this party problem is also known as the independent set problem. And we're going to say that a set S, which is a subset of the vertices, is an independent set if no two nodes in S are joined by an edge. So no two nodes. So for example, we can take one of these two, either this one or that one. We can take, let's say, that one, and that one, 3 along that path, and that allows us to take, so this gives us 6 people that we can seat at a table who will all mutually get along. So given a graph G, our goal is to find the max independent set, the max set of people we can put at a party. Now, I'm going to describe another problem, also related to graphs, but not exactly the same. And this, if you recall from class, was a generalization of baseball. So in baseball, we have a diamond like this, and we have a few bases, and everybody has to run like this. In cricket, we have an even simpler graph, where you just have the wicket and what's the other side called? The crease? And you just run between these two. So it's an even simpler graph, and I would like to make baseball with a more general graph. So we'll have a home plate, and we'll have a bunch of bases, and anybody who basically goes through, makes a cycle, a non-trivial cycle through this graph, starting from this node, scores a run. So the problem will be, how do you defend such a graph? And in particular, you want some defender on every edge, so that if someone is running along that edge, you can possibly tag them. So in this particular graph, of course I can cover them all, and then I would defend every edge, but you want the smallest such set. And in this case, there exists a solution, I think, of size 5. So that edge, 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 this edge, this edge, this edge, this edge, this edge, this edge. So this group of 5 defenders will cover every single edge in the graph. So a vertex cover of a graph is a subset S of V such that for each edge, either X is in S or Y is in S. A vertex cover. You want to cover the graph so that every edge in the graph has some node that's in your cover. So here we go. So the goal is going to be, given a graph G, find the minimum size vertex cover for G. And what I want to show you is that this maximum independent set problem can be solved by solving the minimum vertex cover. So in particular, the VC problem is as hard as the independent set problem. When you see this notation, max inset is less than or equal to min vertex cover in O of V time, it means that a solution to man vertex cover plus O of V time leads to a solution to the max inset problem. And so what I want you to do, in order to show this, what we need to do is take an instance of independent set and solve it using vertex cover. So on the left here, we're going to have an instance of independent set. We're going to have a graph G, and your algorithm right here is going to transform it into an instance of vertex cover. Now, any solution to the vertex cover, it's going to be some set S. Your algorithm is going to have to change it into a solution, and in particular, this algorithm is going to take O of V time, in addition to this solution time. So the most important conceptual part of these reductions is getting this picture right. That's the first step to doing this type of thing. And then once you have the picture right, then we can work on how to actually show the reduction and how to prove it. In this case, I'm going to, just like with every other example, I'm going to start with a very simple example. It turns out I'm going to show the theorem set S is a vertex cover of graph G if and only if V minus S is an independent set. In this case, the problems of vertex cover and independent set, although on face slightly different, and the way I describe them, one is like about parties and one is about baseball, they didn't seem like they were the same problem, but it turns out that I'm going to prove to you that essentially taking the complement of one answer is the answer to the other problem. As a very high-level overview, look at this particular graph. This right here I claimed was this is an independent set. Yeah, and this is the VC. Okay, so let's go ahead and prove this. Suppose S is an independent set. Consider any edge, which is x comma y, in E. We want to show that V minus S is a vertex cover. So how do we show a vertex cover? We have to say for every edge in the graph, one of these two nodes has to be in V minus S. So consider any edge, x comma y. In case 1, if x is in S, that means that y is not in S, because S is an independent set. And if y is not in S, that means that y is in V minus S, and so edge E is covered. Now consider case 2. Suppose x is not in S. Well, this directly means that x is in V minus S, which means edge E is covered. So this implies V minus S covers every edge in G, and so V minus S is a vertex cover. Like I said, this was a very simple example. The definition of independent set and the definition of vertex cover are complementary naturally. And so one just has to point this out to show that a solution to one is a solution to another. Let's go the other direction. Suppose Vs is a vertex cover. We need to show that S is an independent set. So I'd like you to spend 4 minutes with your partner and try to finish that argument. What's the first step we need here? Suppose Vs is a VC. We need to show that S is an independent set. So what do we need to consider? Consider an X that's in S. Okay, what do we need to show that S is an independent set? We're going to consider some element X in S, and consider any edge x comma y in E. What's our next sentence? Yeah, so in particular, since x is not in V minus S, but V minus S is a vertex cover, this implies that y must be in V minus S to cover edge xy. So this implies, in particular, that y is not in S, and this holds for any V in V and any edge V comma W in E. So this implies that S must be an independent set. Okay, so let's draw that into our picture. So our picture was we had an instance of min vertex cover, and we translate it by doing nothing, and that gives us an instance of max independent set. And we solve this using any solver for independent set, and we're going to get some independent set S. And now all we do is we compute V minus S, and that takes order V time, and we're going to get a vertex cover. And so this in particular shows that VC is as hard as independent set. Now you can just run this entire argument with sides flipped, and that would show that independent set is equal to vertex cover as well. So these two problems are literally equivalent. They're equivalent up to O of V time. We're going to move to a slightly more interesting one. I'm going to introduce this logical problem. It's called the 3-sat problem. It's extremely general, but its definition is very hard to motivate. It's actually purely logical. So the input is going to be a formula in 3CNF form. And that means it's going to be a logical AND of clauses of 3 variables. It's going to be a logical AND of clauses of ORs of 3 variables. Okay, so the formula is going to be A or B or C and not A or D or F and etc. So these are what are called the clauses, and these are what are called the variables. And there are 3 variables in each clause, and they're all ORed together. And the output is going to be an assignment which maps the variables to true or false such that the formula is true. So let me give you an example of one of these. Here is a formula, x or y or z, and x or not y or not y, or y, and u or y or not z, z not x, u, etc., etc. So this is a 5-clause formula, and we often use the Greek letter phi in order to stand for a formula. And given a formula like this, we'd like to find an assignment A, which maps x, y, u, and z to different values. So I believe if we set this to be true, this to be true, this to be true, and this to be false, then we can satisfy this formula. So for example, since x is true, this clause will be 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 true, and this clause will be true. So this assignment satisfies all of the clauses of the formula, and so it's a satisfying assignment. Many of you have likely seen this problem in 3102. So here's my first question. I would like to show that 3-sat can be solved by solving independent set. In other words, independent set is as hard as solving 3-sat. So the first thing I want you to do is, with your partner, in 2 minutes, draw the diagram which I had before, with boxes, your blue box, and fill in those boxes with what goes where. So what goes in this black box right over here? What problem goes on the black box? 3-sat. Okay, great. So we're going to have a formula 3-sat, and we're going to have to map it into a graph G, which is an instance of independent set. We would solve this and get a set, S, and we have to map this back into an assignment A. So this is the outline of what we have to do, and this is how we do it. And a lot of these reductions, they used what are called gadgets. These gadgets are ways of encoding the constraints of one problem in terms of another problem. So let me give you an example. Keep in mind this color map right here. We're starting with something with yellow color, and we need to map it into something of orange color. So we're taking this formula right here, which is a yellow formula, and what we're going to do is map it into a graph of independent set. So this is your first non-trivial reduction. We're starting with something that's purely logical, a formula, and we're going to something that's a graph. Now here's the insight. A triangle has a very special kind of independent set. What is the size of the independent set of any triangle? It's 1. You can only pick one of the nodes because obviously if you pick another one, they'll be connected by an edge. And so this reduction is going to take each clause of this formula and turn it into a triangle. So for example, in this case, we're going to turn it into x, y, and z, and this triangle is going to be x, not y, not and y, u, y, and not z. We've solved one aspect of this problem. If we pick an independent set here, we're going to have to pick one node from each of these categories. If we want to satisfy each clause, that means we need to pick one node, one variable from each clause, and assign it to be true. And so we can make a triangle for each of these clauses. And if there is an independent set of size k, then that means we've satisfied each of the clauses. So we're going to map each of these clauses to a triangle. The triangle are going to be notated with the variables in this clause. And now an independent set is just going to pick an independent set of variables. That means it's going to pick one variable per clause. And that's the variable we're going to assign to make true. Question? Yes. So the next question I was going to ask is, what is wrong with this argument? Exactly. So notice we could have selected this x value right here, and we could also have selected this variable not x. That would have been an independent set of size k, but that doesn't represent a satisfying assignment because you can't have x true and not x also true. So we need to add edges to this to ensure that we do not come up with an invalid assignment. What kind of edges can we add? Question. That's right. That's right. That's exactly the solution. So we take x right here and we map it to every instance of not x. Similarly, we connect y with every instance of not y, and z with every instance of z. So let me go ahead and just get to the answer here. So now, if we selected a value x, that means in particular in any other clause, we cannot select not x. So this is the first part of the argument. We started with something yellow, and we mapped it to a graph G that's orange. So this is how we took phi and we mapped it to a graph G. We still have a bit of work to do. We have to show that if phi was satisfiable, which means there exists a satisfying assignment, we have to basically show that there exists an independent set of size k. I haven't defined k yet, but this right here, phi, has k clauses, and we're going to map this to g comma k. So we want to see if there's a independent set of size k for this graph G. So if phi is in SAT, there exists a satisfying assignment for phi, and that means each clause has a true variable. Pick one true variable per clause. Right? So in this case, x, x, u, u, z. So we're going to define S to be the one true variable per clause. We're going to argue that the size of S is k because there are k clauses. And if a variable in clause I is selected, then its negation is false and not selected. Similarly, one node per triangle. If we select only one node per triangle, that means that the two other nodes are not selected, and so there's no violation of the independent set property. That's fine. Pick one of them. X and Y are both true in this example. I picked X. I could have just as equally picked Y. That would still lead to a vertex cover of size k. That would still lead to the property that if Y is selected, then not Y is not selected in any of the other. Each clause has a true variable. This is because there's a satisfying assignment. Has a true variable. There can be more than one. We're just going to pick one of them, and that will lead to an independent set. The argument in the other direction, if GK is an independent set, by definition, only one node per triangle is selected. Make that variable true. Assign any unassigned variables to be true as well. So I'm going to say the resulting A assigns every variable. The assignment A is consistent because if A of x is true, then no vertex for not x is in the independent set, and so x naught is assigned false. And the final property I want to make is phi is satisfied by A. Why is phi satisfied by A? Why am I doing this right here? Because an assignment, by definition, needs to have a true or false for every variable. Yeah, so I meant the positive version of any unassigned variable to true. What's nice about this theory is that many problems can be related in polynomial time to one another. So I mentioned 3-SAT, and we discussed how 3-SAT was equivalent to independent set. These type of reductions are known for hundreds and hundreds of problems. I'll give you an example of clique in a second. Clique and vertex cover and independent set and set cover, they're all sort of related. And then we'll make a statement about this very large set of class of problems and show that there's actually a much more general class of problems which are all can be reduced to any of these problems. And so these problems are as hard as a very large class of problems called NP problems. Let's talk about this problem right here, clique, as another example of reduction. So you're given a graph like this. This can, for example, be a social graph. So one problem that Twitter has is that they have many business problems, but in terms of computer science, one of the problems they have is that they would like there to be very easy to sign up and for many users to be able to say stuff on Twitter. But they don't want the entire network to be full of robots which just like each other and try to upvote their own stupid comments. So they want to try to prevent bots and fake accounts from polluting their network. And so they have this problem. They have their social graph, which consists of 100 million, maybe today it's only 90 million, maybe it's growing down, but still it's several million users. And you have, of course, all the people that you follow, which you can represent with links. If you were an attacker, what you typically do is you create like 1,000 accounts by basically creating 1,000 bogus email addresses and just hiring people to register your account and register some bogus type of thing. And then what you do to make this 1,000 users valuable is you connect them to each other. right? You make them all friends with one another. And then when one of them says something, what you do is you have your other bogus accounts slowly retweet the thing that first account said, and then like the things that those other people retweeted, and etc. This would basically fool the Twitter algorithm into thinking that this is some sort of topic which is newsworthy, because it's slowly getting a lot of retweeting and liking. And so that's a way to game one of these Twitter social algorithms. What can Twitter do? They recognize that most honest people, they have very large and disparate social networks. So you have the friends that you made in high school from different parts of Virginia or different parts of the United States. You have those people that you met at that one Coachella concert last summer. Then you have all the people that you met in Europe when you were there last summer. And of course, all your summer internship friends. And so you have many social networks. You have little social networks, and your network connects to if you take 4 hops from your social network, it'll typically get to a very, very large set. Whereas if you're an attacker, what your social network is going to look like is something like this. Bob is friends with Alice, Carol, and Dave. Dave is friends with Bob, Alice, and Carol. Carol is friends with Alice, Bob, and Dave. Right? They're all friends with one another, and in this case, they have a few external links. Like, for example, they did this type of attack where you follow some random person, and out of social politeness, they sometimes follow you back. But in general, a social network that is just a clique like this, that's a small clique, that's a pretty good sign that with no other external edges or very few external edges, this is a sign of a rogue set of accounts. And so a more generalized version of this algorithm was actually run in 2013 to weed out several million bogus accounts on Twitter. Now, of course, Twitter now has this sort of dilemma inside, whether they want to keep those accounts because they make their numbers sound better, or whether they want to eliminate those accounts and try to make their network a little bit more robust. But the problem we're going to consider is that you're given a graph G and a value K, and you'd like to determine if G has a clique of size K. And by that, a clique means a complete on K nodes, meaning all K vertices are connected to each other. Now, of course, there are also very good reasons to find cliques. You can also mine a lot of intelligence from a social network by identifying cliques, because naturally there are good reasons for cliques. Because your study group, for example, you're probably all friends with one another. It's likely that on Facebook or a social network on Snapchat, you're all going to be friends with one another. An advertising problem might be, hey, let's find natural cliques in graphs, and then let's try to, instead of spending our ad budget on targeting all of them, what we should do is first target one person in the clique, and presumably let's try to pick the influencer. So whichever the person in that clique that has the most friends, or like has some evidence of always posting selfies, etc., they make some sort of psychological assessment of which the influencer in that clique is, and then they'll say, you know what, we're only going to spend our ad budget on the influencer of cliques. So let's take this huge social graph, let's try to break it up into cliques, and then when, who knows, when some sort of new hip object, as you can see, I'm not in the market for those, so I can't even come up with a positive example of one. So when something, I thought in those 10 seconds I could come up with something, but, and they're going to find the influencers and try to target a bunch of ads. Boy, you'd be so cool if you had a Tesla. Look, the wing, the doors, and everything. They're going to target you, and to maximize their ad budget, they're going to do that here at Virginia with all the influencers here, and then at the other schools, the influencers there, et cetera, et cetera. So we all understand what the clique problem is and why it actually reflects some natural computation that people would want to do. Let's go through this example. So we have, what we'd like to do is we'd like to show that 3sat can be reduced to clique. Okay, so clique is as hard as 3sat up to polytime. And this up to polytime means it takes polynomial time to transform the instances. So if we have an instance of 3sat like this, we'd like to turn it into an instance of clique, and we are again going to use a gadget to do this. So here's what the gadget is going to be. If this formula has k clauses, we are going to turn it into a graph and a k for each of those clauses. And here's basically how it works. So for each of these clauses, we are going to create the 3 nodes. So for example, x1, x2, x3, x1, x2, x3. Here was not x, not x, not x3, and etc., etc., etc. This is going to be very similar to the independent set problem we had. So now, which nodes do we connect to each other? We're going to connect x1 to every node that is not its opposite. Similarly, we can connect x2 to every node that's not its opposite. So for example, like this, and x3 to all of its not opposites. So this is the graph that we construct. And now, what if graph G has a k-clique? What does that mean? What does it mean for this graph to have a clique? The observation I'd like you to make is that if you have a clique, in this case a clique is just 3 because there are only 3 clauses, but if you have a clique, basically you have a consistent assignment which makes each of these clauses true. So for example, if I've selected x1, I can make x1 true. And that's because x1 is only connected to nodes that are consistent with x1, right? You don't connect x and not x. And so this means you can make x1, you can make x3 true, and that will make this clause true, and you can make x2 true, and that will make this one true. And so a k-clique selects a variable from each clause to make true. The variable will be consistent because its assignment will not conflict with any of the other assignments, just like the independent set. No, see, look, x2 you can connect to itself. So here's another assignment which works, because x2, x3, and x3, that right there. So I can connect x2 to x2. That will satisfy these 2 clauses. They're consistent assignments. Just like with the independent set, we have to assign the other variables to be, their positive versions to be true. They don't actually contribute to the satisfiability of it. Did I answer your question? That's right. So for each of these clauses, you do not connect these clauses to each other. You just connect the variable x1 in this set of 3 to all other variables in the other gadgets which are consistent with it. Perhaps I wasn't clear in the way I construct this. I take each of the variables from each clause and I put them in a little column or gadget. Okay, like this. Then I do that for every clause, and then I connect the nodes to non-opposites. So what I mean by that is, by this picture, I connect x1 to every other variable in the other gadgets which are not the opposite of x1. So if, in this case, the not x1, I'm going to connect to x2 and x3 later on. Let me get to the highlight of this. What we're touching upon is this theory of NP completeness, which you'll learn about in 3102. You'll spend, hopefully, several lectures on it. And the very basic idea is that we're going to skip this one detail. In 3102, you talk about everything which are sets of instances. So a language is just a set, and in 3102, instead of talking about the algorithmic problem, you're just going to simplify by saying, is this element x in L? That's a question. The algorithmic question you're going to consider there is, I give you an element, is it in this language or is it not? And it turns out that that problem is essentially, the search problem reduces to the decision problem. So if I actually want to find a vertex cover for this graph, and I have something which tells me whether this graph has a vertex cover or not, I can play a version of 20 questions by removing nodes and asking, does this have it, does it not? It's in fact what many of you do in office hours with me. You say, is this the answer? Okay, no, let me change one thing. Is that the answer? And you essentially get to the solution. And that's the same thing that one can do in general, so I'm very happy that you do that because you're actually implicitly learning this search to decision reduction. But what we do, we can define a set of NP, and this is a formal definition, but I want to give you the intuitive definition. A language is an NP if you can efficiently test whether the answer is correct. So, for example, a question of me proving that I have a brother, that's something which I can prove to you very efficiently. I can have my brother stand right here, show you the birth certificates, or do a DNA test between the two of us. That's a pretty efficient way to test that I have a brother or a sister. But there are many problems which you can prove that a solution is true, like all of the things we've talked about. Satisfying assignment. I can give you the assignment, you can test it really quickly. Vertex cover. You can look at the nodes and check every edge, you can test it. You know when something is beautiful or when it's not. NP completeness. A language is in NP complete if it's in NP, so you can test whether it's correct or not quickly. And additionally, every problem in NP can be reduced to L. So Cook and Levin showed this very nice theorem. And this nice theorem basically says that if your language is in NP, then you can solve it by solving 3-SAT. This takes several lectures to cover in 3102, but it's a pretty beautiful argument. And with that, one gets this very nice algorithmic picture of all of the problems. So all of the problems which you can check whether they're correct efficiently, you can reduce them to 3-SAT, so you can solve it if you could solve 3-SAT. And then many of the problems that are natural, like Twitter's problem with finding bogus people, your party planning problem, many data compression problems, FedEx problems, traveling salesman problems, many problems you encounter in real life, they turn out to be as hard as 3-SAT, which in turn happens to be as hard as this large class of problems. And so far, we don't know whether there are efficient algorithms for these things in NP. All of the algorithms we have for these type of problems are exponential at least. Okay, I will see you on Thursday.